So I would like you all to give not a first-time presenter, but a first-time ShmooCon presenter. Welcome to Bryan, who will be speaking on CacheCrashers, exploiting and detecting vulnerabilities in Memcached. So please give a warm ShmooCon welcome to Bryan.
Hello. Thanks for being here this evening. A little bit about me. I am BryanAlexander. I currently am a security engineer at Stripe, working on bug hunting and penetration testing and other vulnerability custodial duties. Formerly, I was the R&D lead at FusionX, which is a red teaming firm, and I'm a recovering Windows exploit dev. So just a quick agenda for today's session. We're going to talk a little bit about what Memcached is, why Stripe uses it, and why we are looking at it internally. Fuzzing Memcached, what we did to build a fuzzer for it, and some of the results that we found. And then detections. So once we're able to find vulnerabilities and potentially weaponize them, how can we kind of detect them at scale and detect them broadly within the enterprise? So Memcache, if you have prior intuitions about how caching works, you'll find that those apply here quite generally. Memcaching is kind of an old guard industry standard as far as caching servers go. It traditionally sits alongside your clients as well as your data stores. It was developed for LiveJournal circa 2003 and originally written in Perl, as all good things once were. And then a couple years later ported to C, as all good things now are. It is RAM only, because if you're swapping to disk, that's going to kind of defeat the purpose of using caching, and it's expensive. It's key value stored, so it is accessed with a key, and then you get the raw data back. It is agnostic to the data that you're putting in there, so it doesn't understand data structures, so everything needs to be serialized beforehand. It is functionally distributed, and that effectively means that half of the implementation lives in the clients, and the other half lives within the servers. The servers are a bit solipsistic. They believe that they're the only servers in the world, and so if you want to facilitate contact between servers, you need to build extraneous infrastructure. And then finally, it is forgetful by design, as traditionally a lot of caches are. Memcached is a least recently used LRU cache, and so items expire within the cache, and the memory within it is reclaimed lazily on access. Memcached can be spoken to over a number of different protocols, namely TCP, UDP, or a local domain socket, and then it has kind of its own protocol definition for actually interfacing with the service. It has 3 of them: binary, text, and meta. Binary is deprecated and no longer recommended for use. And then there's the text and the meta. Meta is the current recommendation, and it is essentially just a subset of the text-based protocol. On the right-hand side there is kind of an example of how you can access it. So this first one right here is just an MS, which is a meta set. And then the key is test key, and then we're storing 2 bytes. Here's our data that we're storing, and then we get the response. Similarly, the MG is just a get, a meta get, returns the 2 bytes that we stored in there, and then a delete, and then a secondary get. Importantly to call out is Memcached follows the Linux philosophy of doing one thing and doing one thing very well, and that's what I think Memcached excels at. It does not have a lot of built-in or baked-in infrastructure kind of by design. So as far as encryption goes, it doesn't have any encryption capabilities for all the data at rest. That has to be done outside of that. It doesn't support mutual TLS, but it does support TLS for connecting to the server that can be compiled in, and it is currently experimental. And then it does not have a strong authentication or authorization system built into it, and so it has SASL, but that is effectively it. And the target for some of our work internally was in the Memcached proxy component specifically. This is, if you think of just a traditional TCP proxy, shoveling data from one socket to the next, That's what the Memcache proxy does, but it has a lot of smarts built into it, so it can actually speak that meta and text-based protocol, which allows it to do a lot of interesting routing that can be completely configured and hot swappable based on the implementation of it, which is all in Lua. This was added very recently. Early 22 was when the initial commit hit for it, but it didn't actually go production until early 23. And this was about the time that we were scaling up some of our caching infrastructure using Memcache, and we wanted to kind of take a holistic look at Memcached and the Memcache proxies, since it hadn't really had a lot of previous attention by the community before then. On the right-hand side here, you can see what kind of this Memcache proxy definition looks like. Here, it's just defining two different pools. This one is named foo, and this one is named bar. So any meta set or meta get to a key that's kind of in the path of foo whack key is going to be routed to those backends, and then similarly with the bar can be routed that way. And so this allows for a lot of dynamic flexibility in terms of how you're routing specific requests. So for example, you can route read requests to one set of pools and write requests to one set of pools. You can, because it's all in Lua, and you can just send the process a sig hup and dynamically update all the routes. You can do automatic failovers, stuff like that. So Memcache at Stripe, I wanted to, doesn't look very good over there. As I kind of mentioned, we're looking to scale up our implementation. Memcached is kind of functionally distributed, so we had to build a lot of custom supporting infrastructure to kind of grant us a lot of the primitives that Memcache doesn't have out of the box, like authn and auth. At the top here, you can see all of the clients. These are clients that Stripe has built internally that we then expose to all of our product teams that want to leverage our caching infrastructure. These route over to the router layer, which is where all of the Memcache proxies live. These first hit an auth service, which is where we can do logging, we can enforce authentication checks, mutual TLS, and then we can perform pool-based authorization checks based on the requesting services. So once we get through all of that good stuff, we hit the Memcache proxy, which is just the implementation of Memcache proxy that Memcache provides. And then that speaks directly to the actual Memcache data pools based on whatever the request is and whatever the routing definitions are. Importantly, also here to note is that we have sidecars running in every single router and data node, and this gives us health checks and visibility into how our Memcache services are performing, but then also allows us to perform some of the topological updates to the actual routes on demand. So fuzzing Memcache, I mentioned that Memcache is written in C. It has its own protocol that it built many, many moons ago, and it doesn't use anything clever like protobuf or any of those standard definition libraries, and so it was kind of a ripe area for probing. Unfortunately, Memcache is compiled as a single monolithic executable binary. It does not provide itself as a library, which makes kind of pulling apart the proxy from the rest of the application rather cumbersome and difficult. There are a number of different threads that it kind of spins up right out the gate, as well as using kind of a complicated lib event internal protocol for transitioning between the different threads and queuing some of the slab maintenance and the LRU maintenance and triggering from the socket data that it's receiving. So it's kind of a mess. Essentially, down here at the bottom, if the colors show up, which they don't kind of. Anyway, the server socket, which is the TCP or UDP or local domain socket, that constructs a connection object, which kind of stores all of the information that the incoming connection needs. It attaches a lib event file descriptor, and then it passes it to one of the available MC worker threads. And the MC worker thread is essentially the thread that's going to be working on it. So trying to fuzz this while focusing on the functionality that we're interested in and not taking on the overhead of all this other stuff was a little bit difficult. But this is kind of a little bit of what pseudocode of how we were able to do this. And so we used AFL. And if you're familiar with AFL, you should be familiar with what this is doing here. But this is essentially an initialization function where we can link against some of the object files created by Memcache during compilation, and then we can kind of instantiate some of that necessary proxy code that we need to be able to fuzz it in a very targeted way. And this is also nice because we can kind of scale our fuzzers through not only CPUs, but also within each session. So we can scale the MC worker threads and create any number of different connection objects, attach our fuzz binary data to it, and then let it churn. And then this is what, I'm not sure if it shows up there, but this is what one of the inputs looks like once it's being fuzzed. So down here, we're just allocating memory out of our MC worker. We're passing or memcopying in the fuzz data that we're getting from AFL. And then we're passing it to this try-read command proxy. And this is essentially the entry point for all proxy parsing code. And what's nice about this too is we can just use this same structure, swap out the try-read command proxy for try-read command text or binary, and we can fuzz kind of more sophisticated some of the protocol parsing code that they have in there. And then of course, we're gonna look at some of the results of that. I think anyone that uses AFL is contractually obligated to include this slide in their presentation, so here it is. But I draw your attention to a number of different things. One is the stability down here is 100%. And if you're not familiar with what that means, it essentially means that the same input produces the exact same call graph in between runs. So there's no non-determinism in here that might affect the mutations and exploratory capabilities of AFL and AFL++. And then additionally, we're running at about 4,000 executions a second, which is pretty good. And this is all on a single CPU with no scaling whatsoever. So as you can imagine, this scales quite well. And then this was kind of a contrived screenshot, so it doesn't really capture all of the findings and whatnot that we had. We started out with a corpus of about 20, which was just us taking a dictionary of the protocol definition that we get from Memcache and then kind of building our own dictionary on that. So there's about 20 of them, and then over time, I think our corpus grew to something like 1,500, which we just kind of continued to groom over time. After about a week of fuzzing, we identified about 80 different crashes. A lot of these were kind of root caused to the exact same issue. Some of them were not reproducible due to all of the threading and some of the heap memory and allocations there. So what we kind of did at this stage was triage those vulnerabilities and then identified one that we wanted to try and create a POC for so that we could deploy it in our environment, and we could start building detections based on that to kind of evaluate holistically the efficacy of our detection capabilities. So we're going to look at one of those bugs briefly right here. One of them that was in the multi-retrieval commands, which I'll mention in a moment, was a stack-based buffer overflow, and this was a very classic memcopy into a stack-based buffer that we could push too much data into. Over here you can see I believe you can see the register state at the time on a 64-bit Debian box. We overflow notably the connection object itself, and then we have full control over the stack, the base pointer and the stack pointer. This was all, importantly, this was all crashing within the proxy itself, so it is not hitting any of the upstream data nodes. This was fixed recently in 1.16.22, which is the latest release of Memcache. And just to kind of drill a little bit more into how this vulnerability works, is this right here is what a post-tokenized request looks like when there are multi-gets, which is essentially just multiple gets packed up into a single request. Memcache will tokenize these based on non-space characters. So in here we see we have two GET requests, one for a key of A and then one for a key of B, and then terminated with a new line character, which is how memcache terminates. And the way that the copying into the buffer and then processing this works is it first checks if the key is of requisite size, and then it mem copies into buff, which is a small stack allocated buffer. It copies in the command up to the next token index. And then it copies in the key into that same buffer, and then it processes it as one request, and then recursively does that over the entirety of the packet. But what happens when you pack in a whole bunch of spaces in here? Well, it does a similar thing. It checks the key length, and then it mem copies that command up to the next token into that buffer. So as you could probably intuit, you just add a whole bunch of spaces until you get to the maximum buffer size. And then in your keys can be arbitrary text data, and you put that in there and gain control over the stack. I won't go too in the weeds on exploitation of this one, but it is, if you're familiar with stack-based buffer overflows, you can use a simple ret to libc here. If you'll notice down here in the gadgets, we have hard-coded addresses in here. This was done, we had a number of PI, or a position-independent executable, which is leverage ASLR. We found a couple info leaks, which would have allowed us to bypass that, but they were all in kind of quirky and non-default settings. So we didn't pursue it, and for kind of the sake of our tests, we just hard-coded some of the addresses in there. As I kind of mentioned in the register slide, we had control over the connection object itself, and we could do that without actually overflowing the stack pointer. If you're familiar, again, with stack-based buffer overflows, you'll know modern systems have SSP or stack canaries, which are just unique little tokens on the stack that are checked prior to returning, and if it doesn't match what the expected value is, then it's going to throw a runtime error. So we identified a arbitrary address write using this connection object, which would allow us to bypass that, but also allow us to bypass partial rel row, which is another complicated mitigation on modern Linux systems that prevents writing to the PLT or the GOT. But we could use the arbitrary address write to kind of get through some of that. This was less trivial on more modern systems compiled with something like fortify source, where there are bounds checked mem copies. And so we didn't pursue that route because we didn't deem it necessary. So very quickly, kind of running through detection of what this looks like. So once we are able to build a POC that runs in our environment that we can use to compromise a memcache proxy, we wanted to see what kind of telemetry we can get. So one of our crude examples is assuming that an adversary's payload is going to fork and do something, whether it be run bash or run netcat or run some other executable on disk. That's one way. But attackers are, of course, under no obligation to fork off, and so this, of course, will miss anything that doesn't fork. So if you stay entirely within memory and use another process as a puppet and run your commands from there, or your DNS exfil from there, then this will not work. And so a less crude way is to effectively re-implement the tokenization that memcached itself does of the requests, and then validate that the gap between the key and the tokens are less than the overall size. So if you're familiar with Suricata or Snort, this rule should look kind of familiar. This is just checking for data packets that exceed 284 bytes and checking if they start with get. And if they do, then we execute this Lua script. And the Lua script, essentially, I won't go through it, but essentially just walks the entirety of the request, looks for the spaces, and then calculates the distance between those. That way, if you have the capability of deploying a network-based signature, and you can sniff all the data on the wire, then you can capture it regardless of what behavior an adversary or the actual exploit is running on the system itself. Really quick takeaways from some of our results. If you're running memcache or any fork of memcache, I recommend updating it, of course. And two kind of what might seem as obvious points to fuzzing aficionados, but maybe more relevant for students that are in the audience, is really knowing your target in depth can provide a lot of effectiveness in fuzzing, even for hardened targets. The more novel your approach is and the more fine-tuned and directed you can make it, the better the results are that you're going to have. And a software update. Where to find more? We're going to be releasing the detections and the POC and the slides and everything on Stripe's public GitHub in the coming days. And then I wanted to quickly mention and give a shout out to Google and their OSS Fuzz project. If you are not familiar with OSS Fuzz, it is effectively free infrastructure that Google provides for fuzzing open source code. So if you have anything that's built in C or Java or Python or anything that could benefit fuzzing, Google will provide all of the infrastructure for doing that, all of the CPUs, all of the code coverage mechanisms, all of the updates, all of that free of charge. So we took the fuzzer that we built for the proxy, and we got that looped into OSS Fuzz, where it is now fuzzing continually. I don't believe I have any time for questions, but if you have questions or want to chat about Stripe or fuzzing or memcached or anything like that, I will be available in the lobby after. Thank you.